We're going to talk about driven elements and Yagis and a variety of things that people think are true about Yagis. Hopefully we'll improve a variety of things here. This is the optical equivalent of a Yagi. The light bulb represents the driven element. We have a mirror in back. We have a lens in front. And electromagnetically, wave-wise, this is the same thing the Yagi is doing. Adding another reflector doesn't help, but we can add more lenses and change the focal length and improve the gain. There used to be some times when they would have multiple reflectors on the Yagis. You will note virtually all the modern Yagis don't do that anymore. Primarily, that was correcting other issues with the antenna. Here's something I've run into several times. Here we have three Yagis. One has what I would call a normal driven element in the middle. On the top, you'll see that the driven element is longer than the reflector. Therefore, all the waves tend to go around the reflector and go out the back of the antenna. Down at the bottom, we have one where the driven element is shorter than the first director. Therefore, the waves can't get and go around the directors, and that just doesn't have any forward gain. Yes, I've had people actually tell me this. In reality, the driven element is exciting the Yagi, and if you built these three and tested them on the antenna range, they would perform identically. The length of the driven element has a lot to do with getting a good impedance match and a good SWR, but does not change the pattern. The other thing I want to bring out point is for some of you will already know, if I have two antennas looking at each other, then the area between the two antennas is essentially a transmission line. Many of you know that the impedance of that transmission line is 377 ohms. So the universe has an impedance of 377 ohms. So your antenna is really a 50 to 377 ohm impedance transformer. And we'll kind of be bringing that up in some of the other topics we'll be bringing up. We'll start with the good old driven element. Impedance, 70 ohms, give or take. For those who want to be more precise, that assumes the diameter of the element is infinitesimal. As you start coming into more realistic diameters, it drops down a little bit, but 70 ohms, give or take. Here we have one where we just simply have two dipole elements, two reflectors, and this ends up being a nice simple dish feed. Here we have another one, which was a multi-Yagi antenna. We have driven elements tuned to two different frequencies and interlaced elements. This one was actually listening to telemetry transmitters in the stomachs of cows. Here we take a driven element, we have what we call the beta match, where you have a short stub. The short stub behaves as a capacitor, so it's a capacitance tuning element. You can take the stub off and replace it with a high voltage capacitor if you'd like. Here we have one on an antenna. You can see the stub here. For those of you who like to go to Friedrichshafen, you may recognize the roof of one of the halls there at Friedrichshafen. Great place to photograph antennas, lots of them around to photograph. The folded dipole. Impedance somewhere between 2 and 300 ohms, depending on what the diameter of the material is and the spacing between them. Here we have one. Now, what I can do is load this down, as 300 ohm impedance is pretty high. By bringing in the other elements very close, I have a loading effect on the driven element, and I can now actually bring it down to 75 or 50 ohms just by the spacing effects of the other elements of the antenna. And this can make for a very simple design. Here we show if you have 72 ohms, the elements are going to be much further apart. If I have a high impedance 300 ohm line, the directors have to be very, very close and become very critical in both spacing and length. but you can now get your impedance matching with the physical characteristics of the Yagi itself just by doing your spacing properly. Something we're starting to see on HF antennas, especially the multi-band ones, what they call the offset fed dipole. If I feed it right in the middle, you get around 70, 75 ohms. As I start moving off towards the edge, the impedance goes up. In theory, if I had it exactly from the edge, the impedance would approach infinity. But right in here, I can now go 75, 100, 200, 300, whatever I want, just by changing the spacing. Here we have an example of a monopole, and you can see where they have moved up where they do the attach point to change the impedance. Here we have a rather robust Yagi, and you can see on the driven element where they have separated it out and they're actually feeding it up in this area. So by feeding it up in here, I can pick out again whatever impedance I want to get me a match to the other elements. Here's a Cushcraft Yagi, where again, they've done the same thing. They have a sleeve in here. The coax comes up and attaches at the point that gives them the best impedance match. Schematic representation of the gamma match. I am not a fan of the gamma match for a whole bunch of reasons. You have a series capacitor and inductor tuning, and this can behave as an antenna tuning element. There was a, shall we say, popular AMSAT antenna for many years in the early versions, not today. I've been working with Tim. The early versions, the Yagi was a 465 meg Yagi, 465. But by careful adjustment of the gamma match, you can give it a good SWR at 435 megs. So the antenna had a good SWR. It had an absolutely horrible pattern. Here's an example of a commercial Yagi with a gamma match. We have an outer sleeve. We have a pin going down through the middle, and then we have an insulator. And by adjusting the length of this, we adjust the capacitor. The total length of the gamma match here is behaving as an inductor. So we have an inductor, and then there in the middle a capacitor. I'm missing a photo. I don't know why it doesn't like that photo. Okay. Here we'll go to the one of the T-match designs, again, a very popular one. By moving the shorting elements, I can get any impedance ratio that I want. Again, we go back to the Friedrichshafen, and you can see where you actually have adjustment screws on these, and they can be moved in and out on your shorting bar and adjusted to whatever impedance you want. This is a design that's becoming more and more popular. You're seeing these on a lot of stuff, especially the ones coming out of Asia. The coax comes up through the bottom of the driven element, goes around the inside, and feeds it at the top. They're actually using this half of the driven element as the balun. This is a voltage null down here at the bottom. So they're bringing in the coax at a voltage null and coming across. Neat way to do a folded dipole. Electrically, it looks good. The problem is mechanical. Here, we're going to be having a bit of copper wire pushed into an aluminum tube, which they usually just squeeze. So I've got copper to aluminum. Put that out in the wind and weather, and what do you think the life expectancy of that joint is? So if you ever pick up one of these antennas and complain it doesn't work very good, check it with an ohm meter, and probably need to get out some pliers and squeeze this again, and you can see if you can get a good connection again. Here's an example of one that's on a commercial antenna, and you can see where they have surrounded it with 2 layers of heat shrink tubing to try to improve its weather resistance. Another one which had some problems with weather, and one heat shrink just wasn't enough to protect it. 3/4 of a folded dipole, or I like to call it a jade pole, one that I'm done a lot of particular work with. The coax shield goes to the center of the element, which happens to be a voltage null. So you don't get a lot of RF running on the coax. And then it's fed at the tip here. Impedance is in the 150 ohm range. Here's a commercial antenna, which I didn't see until 10 years after I started using it. But you can see that we have the F connector goes here. Element comes around, reconnects, and this is a commercial UHF television antenna. One of those future projects that I'd love to play with a lot more, you have one driven element down in here, and then it feeds 2 strings of directors. So now I have stacked Yagis, but no power divider. The antennas themselves are taking care of that. I think this has some potential use in several ham applications, especially as we get into UHF and above. But most of the computer programs do not deal with this at all. Project for another day. Here's an example of one for a European UHF television. And you have directors tuned to 3 different frequencies in the UHF TV band, an extremely broad band driven element, and then a reflector, which doesn't have any particular frequency selectivity. Certainly has some possibilities for the ham bands. Here's one that chatted with the guys who were trying to improve it. Again, you have your directors on different frequencies, the very broadband driven element, and they were trying to come up with a better way of doing the driven element. Loop designs, very broad, very wide, makes for really nice broadband elements. In the middle, they have a Ballon coupling arrangement and, of course, some passband filters to keep the GSM television out of your GSM cell phones out of your television. Haven't quite figured this one out yet, but interesting design. Now we'll go to another way of getting your tuning where you actually change the length of the elements on the driven element in order to get your tuning. This happens to be one from Mr. My antenna receives signals and does not hear noise. I got into a rather spirited debate with him at Dayton a few years ago. My comment was that the antennas that you're displaying are not the ones that were in the computer model of your patterns. The patterns and antennas were different. The discussion was regarding the stub matching that he was using here. That stub radiates off to the sides and would fill in the side nulls of the antennas. His computer simulations did not show that. The response was, well, there's no current in that stub, therefore I don't have to include it in the model. If there's no current in it, why do you even have it? And that stub gets quite longer as you go down in frequency. Well, a few years later, he was back to Dayton, and I noticed that he had changed up the Ballon design, and he's now gone to a far more traditional Ballon. You will also note that the driven element is shorter than the reflectors and directors, and that's quite functional. That's not a problem. That's another photo that's not coming up. I have a closer photo up of the Ballon, and why this isn't displaying it, I have no idea. Okay. Another way of doing your Yagis, it does not have to be a rod element. It can be a circular element. This is particularly advantage if I can come up with a driven element arrangement here, which has both vertical and horizontal components. So we can either have a polarization switchable Yagi or one that's circularly polarized. Every year, the Central States VHF Society has a conference, and we set up an antenna range and usually test somewhere between 100 and 125 antennas. We're also noted for people bringing in some rather interesting ringers, and I'm incredibly guilty of that as well. And this is one that was brought into the for testing. Actually, it was developed by a professional engineer and demonstrated 10.5 dB gain. So it actually worked. Research is continuing on the use of DVDs versus CDs. We're also looking at music versus computer CD variations. So research is continuing. Another technique that's used quite a bit in the past, but not as much lately, and this is the only antenna I've seen using it currently, is if I have a multi-band beam, I can take the driven element, especially if we're working with a 2-meter 432, which is third harmonic, and I can drive the driven element as a half wave on 2 meters or as a wave and a half on 70 centimeters. Now I can put in a decoupling stub and couple off just the 70 centimeter energy and use that to drive a 70 centimeter Yagi. So here we have the low frequency driven element. Whoops. Here we have the low frequency, technical difficulties. Here we have the low frequency driven element and the element that couples to it that's very, very close, which grabs off just the third harmonic. This was an application where we were taking a commercial unit and trying to figure out some way of getting additional gain out of it. The computer simulators of having a patch antenna feeding a Yagi is not something you typically see. So I built up this particular test fixture out of low density foam, made elements of different sizes, and played with it on the antenna range, moving things around with chopsticks until we came up with a design that gave us good forward gain. The log periodic, and I'm going to be talking about that a little bit here. The log periodic is the twin booms. You have 2 booms which behave as a parallel transmission line. So I feed the transmission line down here. The signal comes along, finds the elements that resonate. The one behind it is longer, so it acts as a reflector. The one in fronts are shorter and act like directors. So a log periodic is basically a 3-element Yagi on a very large number of frequencies. And when we'll touch on aperture area in a moment, you can think of this as an infinite number of antennas all sharing the same aperture area. But this was applied to Yagis. Here's a Yagi that was made by KLM at the time. And you can see that they have a 4-element log periodic section to the Yagi. It was felt that the very broadband driven element would greatly improve the bandwidth of the Yagi. In reality, we now know that the variations in spacings and lengths, you can get the bandwidth out of the Yagi. The driven element is not a major consideration for there. And this is a dish that's actually part of the tail warning radar once upon a time out of a B-29 and a little PC board log periodic feeding it. Here's another case of where we were increasing the gain of a log periodic. They wanted the total, shall we say, signal picked up of the 2.4 and the 5.8 gig to be somewhat similar. So we have a broadband log periodic. And if I added 2.4 gig directors out here, it would create some issues, but the smaller 5.8 gigahertz directors do not cause a problem. And by adding 5 directors out here, the total amount of energy going back down the coax on 2.4 and 5.8 was roughly similar. Boom to element transitions. This is how to properly do your boom to element connections. Heliarc them. And yes, some minor problems for the hobbyist, but we're going to go into that. When I put the element through the boom, I change its inductance. And as a result, the element has to be longer to compensate for the effects of the boom. Here we have one with the excellent mechanical engineering of a pop rivet in the middle of it holding it together. This works out okay for a while, but you put it out in the weather and you start getting corrosion at this joint. As you get the corrosion, you stop getting the electrical connection, and the antenna director now starts isolating itself from the boom, effectively getting longer. So you put this up as a 450 Mag Yagi. After it's been up there for a while, it's a 440. A little while longer, it's a 430. And they drift down in frequency with time. You really don't want to have a simple mechanical connection. Here's one where it looks like he took a screwdriver and hit it with a hammer twice. Use your favorite 4-letter words in describing this high-level manufacturing technique. And we end up with a lot of different ways to do the boom correction factor. Unfortunately, there's more opinion than data. As we start going into actually looking at what's happening, the ratio of the diameter to the element to the diameter of the boom is important. How big the gap is that the insulator is filling becomes important. What kind of keepers you use holding it. So you can get an extreme amount of variation in how you do the boom to element just on how you decide to construct it. So here you're using these various computer programs, you're analyzing the lengths of elements to 1,000th of a millimeter. Yes, I've seen them published 1,000th of a millimeter. Somebody needs to slap that guy upside the head with a slide rule. So you're really limited as to how you're really doing it. And if you're actually trying to make a super high performance Yagi, you need to measure it. Gunther, DL6W, says you just need to measure it if it's this important. And his suggestion was you build a 3-element Yagi. You have your director out here supported on something that's virtually nothing. A small piece of styrofoam suspended with a couple of bits of string sitting out here, but you know the distance. And then you carefully measure the SWR of the antenna. Then you take your simulated boom element. So this has the material you want, the boom material you want, the keepers you want, and you put it in exactly the same place. Then adjust its length until you get exactly the same SWR. And now you know the real world correction factor for free space element to one using the hardware you want to use. And there's a lot of speculations out there as to what that correction factor should be. But unless you use exactly the same material and unless the guy has actually tested it, be very careful. I purchased this one at Rapid. I just had to bring it back to show it. Anybody care to make a guess what our correction factor is on this one? And I can tell you right now, if you take the little rubber caps off, it moves at about 200 megahertz, just those rubber caps. When I'm on the antenna range, playing with the antennas, I have a tuning stick. So this is a bit of wood with some element material on the end. And as you get it near the tip of the antenna, it'll couple and make the antenna effectively a little bit longer. So you can have a Yagi to start to getting this near the tips. If the gain goes up, the element was too short. If the gain goes down, the element's too long. And you can very quickly go through all the elements and find out what adjustments you need to make. This was a "you've got to be kidding me" antenna at first. Got to meet a East German antenna engineer at one of the EME conferences. And he made the comment, "Oh yeah, get a tightly tuned Yagi and you can take the reflector off. It doesn't make any difference." And I went, "What?" Interestingly, the RSGB is one of the few antenna books that really bring this out. If I'm going to make a 2-element Yagi, a driven element and a director has more gain and a better front to back ratio than a driven element and a reflector. It's just not used commercially very often because it just doesn't make sense. So I had to design one without a reflector. Interestingly, the computer program wouldn't let me do that, but I made the reflecting element about 10 millimeters long, so that effectively did the same thing. And the computer predicted a 40 dB front to back ratio for this Yagi. We took it to the Central States Conference, tested on the antenna range, and it demonstrated 27 dB front to back. So you can do it without a reflector. But this was a tightly tuned Yagi. If you put a reflector element on it, the bandwidth gets much longer, much bigger. This is a way of talking about an antenna that we've been building for RFID purposes that we have not been able to simulate. You're making a Yagi out of very, very fat elements. When you're doing an RFID reader, the antenna is used in both transmit and receive at the same time. So any SWR or reflections are blinding your own receiver. By making very fat elements, we're seeing very low SWRs over very broad range of frequencies. When you take the NEC programs and try to simulate this, NEC does all the simulations as an infinitesimally thin element. It reduces it to infinitesimally thin. If you put in a fat element, it changes the apparent length of the infinitesimal element. So as a short, NEC programs don't simulate these. Some of the time domain programs don't. But we're seeing very broad bandwidths, very low SWRs, and all the work is being done on network analyzers and antenna ranges because the computer simulators don't deal with this. Stacking dissimilar antennas. This is a diagram that has been floating around for years. If you're going to stack a 2-meter and a 70-centimeter antenna, I want to stack them so that the aperture areas do not overlap and they interfere with each other. This is the biggest piece of, use your favorite 4-letter expletive, floating around the antenna world. This is published on several people's sites. I've contacted all of them and found, where the heck did you come up with this concept? Well, I borrowed it from somebody else. I've traced it back about 30 years and I don't know who started it. So if you know who came up with this idea of keeping the aperture areas from touching, please let me know, especially if they're still alive. Well, we knew that this was wrong. So the question is, how wrong is it? At one of the conferences, we brought in 3 reference antennas, one for 2 meters, 220, and one for 70 centimeters. Then we took all three antennas and tested them on all three bands. And this is what we got. The 2 meter on 2 meters had 7 square meters of capture area. On 220, yes, and 432 microscopic. And what you find is the capture areas of the other antenna on the other band is microscopic. So those diagrams really need to look like this. The capture areas are just microscopic for the other antennas on the other bands. Well, does it screw up the pattern? Well, we need to measure that then. So here is a 470 centimeter antenna and a 33 centimeter antenna. These are theoretically first and second harmonics. They're harmonically related. So I started looking at the patterns, changing the spacing between them. Got down pretty close, and you will note that the unused antenna has a 50 ohm load on it, and continued testing until I reached a limit. The U-bolts were touching. Here we have the 900 Mag Yagi. The red plot is the 900 Mag Yagi by itself. The blue plot is the 900 Mag Yagi with the U-bolts touching. Some minor variations in the back lobe, but that's about it. Here we have the 432 Yagi. Red again is by itself. Blue is with the other antenna virtually touching it. It looks like I had a little bit of offset, must have bumped something while I was making the two tests, but again, there's no effect on the pattern. What that aperture area says is the guys on HF who've been using those tri-band trap Yagis for years have to give back their DXCCs because the aperture area says that I can't have the three antennas all sharing the same aperture area. Well, you guys are safe because we've proven that that's a fallacy. Now to take a very major change in the topics. As some of you know me well, know that I enjoy being somewhat of a World War II historian. Oh, well, whoops, forgot. Yes, I've been known to work on antennas of all sizes. These are some 550 meter high antennas, not far from my house. The chap on the left is a director of engineering for a network. They had bought a station here that had problems, and he couldn't get anybody working for him to come up there and help him make some measurements. I just asked him if he was buying lunch. Yes, you got to be pretty good friends to use that elevator going up there. And we decided to have a paper airplane contest from the top. You will note a lot of fuzz in the picture. Those are not compression artifacts. There were 22 television transmitters just above me running roughly 1 megawatt of power. I'm kind of lucky I didn't fry the camera. Okay, now we get into the World War II history. In 1943, they found out they had a problem as they were developing the atomic bomb. The US did not have an airplane that could carry it. Well, we knew the Lancasters were carrying the big tall boys, so we arranged for the UK to set 6 Lancasters aside just for the atomic bomb program, although very few people in the UK knew about it. The problem with the B-29 was you had 2 bomb bays, and it was designed to carry a lot of little bombs. And the ratchet system released one from this bomb bay, released one from this, released one from this, released one from this, and alternated. Between the two was the wing spar. So they couldn't make 2 into 1 because of where the wing spar was. But the Lancaster's got a nice big bomb bay, and it could carry everything. Yes, you had a lot of room for putting big guys in there, and we said, okay. So they set 6 of them aside. They trained out of Eddystone Airfield here, trained for a year and a half, not knowing what they were training for. The biggest issue in the training was the Lancaster did not have the range to make it to Japan and back. So 2 of the Lancs were modified into tankers. This had to be a particularly interesting effort because they would drop out a small line, and the tail gunner of the second plane was expected to catch that, pull it in, and then connect the hose up. Had to have been a rather interesting process. Well, they went ahead and had 15 B-29s modified, or actually built from scratch, with completely different wing spars in them, so that we could actually put these in the special B-29s. Not any B-29 could do it, only the special ones. They had another little tiny problem, and that was the release mechanism. The release mechanism just didn't quite work the way they wanted to, and they bent up a lot of bomb bay doors as the bomb left before they opened the doors. So they contacted the RAF again and acquired several of your G-type release mechanisms. So they did use the Lancaster G-type release mechanisms to release the atomic bombs. In reality, it's probably a good idea that they didn't. I haven't been able to find how high the Lancaster flew while carrying a tall boy bomb, but it had a 25,000-foot normal service ceiling. We know that the Enola Gay released the bomb from 31,000 feet. Also, the Lancaster traveled about 100 miles an hour slower than the B-29. This means that when it released the bomb, it's not pushing it forward as far. Then when it turns around and makes a run for it, it's traveling a lot slower. When the bomb went off, the Enola Gay was about 15 to 16 kilometers from the bomb when it exploded. The Lancaster would have been about 8. I think the lads would have had a sporting chance at survival, but I would not have wanted to be the tail gunner. Lastly, here we have a picture of the uranium bomb. To make sure that it exploded at just the right height, it had a 400 megahertz height-finding radar built into the bomb to set it off. I've always enjoyed the irony that we returned the Yagi antenna to Japan. Neil, back to you.
Right, thank you, Kent. That was an interesting talk. I'll pass it over to John in a moment, because if we've got questions coming in, John will read them out to you. But I've got one question for you myself. Now, you said about these sort of problems with corrosion on antennas, and the bit I remember you saying about corrosion between the elements and the boom. Now, I think virtually all the amateur Yagis that you buy have got the boom held in, the elements held in some way other than being welded into place. What would you suggest would be the best way of actually protecting the antenna? Is it acceptable to sort of put some form of protective coating on the antenna, on the boom?
Yeah, have you gotten me off a share screen yet?
No. No, we're still seeing your first slide, actually.
I'm trying to.
It should say at the top. Sorry. There you go. Your full screen.
We're off. Okay. The technique of having the elements in a plastic insulator where you're separated from the boom and electrically insulated from it work very, very good long term. For what it's worth, all of my antennas outside are painted with epoxy spray paint. That helps glue everything together, keep the corrosion down, and being what's known as battleship gray, cuts down on some of the, makes them low observable antennas and helps down some of the imaginary TVI problems.
Yeah, okay, yeah, thanks. That's useful to know, because I've always wondered what the best way of protecting them. Okay, I'm going to hand over to John G3XDY, who is controlling everything here, and see if you've got any questions coming on the BATC streaming service, John.
Yes, okay, good evening, everybody. I've had a comment from Russ G4SAQ, really great talk, Kent, thanks. Question from Dave, GKQ. Kent, if feeder loss is low, less than 2 dB, what is the effect of poor SWR?
It makes a bad antenna look better.
Okay, any other questions? Please type them in on the chat box on the streamer, and I'll forward them on to Ken.
Of course, we've got about a 30 or 40-second delay before anyone responds, John, of course.
Yes, yes, it will take a little while for that to get through. Yeah. So please type away.
In the meantime, I've got another question for you, Kent, and that's to do with matching at VSWR. You talked about dual band aerials and feeding them from with a single feed. Can the matching ever be as good as separate antennas?
Yes.
Right. Even because one common dual band antenna over here is the which is not harmonically related, is 50 megs and 70 megs antennas driven by.
My host, Sam Jewell, has one up, and I'm tempted to try to acquire one. I have 3 4-meter stations. I have a couple of 4-meter antennas. I'm planning to put them up. I think it would be rather interesting to point JT65 or JT8 back at the UK and see if we get any handling. In this particular area, that frequency band is unused. It's what we call white space. And I'm chatting with Brian Justin, who's the only person I know who has a 4-meter beacon on the air, about going through the paperwork to get permission to set up a 4-meter station. So next summer, when we have some F layer or some E's, it might be interesting to work. And if I don't get the license, I'll just mumble my G8 call, and you'll just say, what was that grid square again?
Yeah.
Right, a question, Kent, come from Mark M5BOP. Kent, any comments on stacking similar Yagis using so-called phasing harnesses?
That is how we do EME arrays, to stack 2 more. I think the biggest I've personally seen is 32 stacked that way. Perfectly valid way to stack them. Exactly what the stacking distance should be is another whole set of arguments. The general rule of thumb is stack them half the boom length. So if you have a 4-meter long boom, stack them 2 meters apart and you'll be pretty close. If they're too close together, you don't get all the gain, but you have a very clean pattern. If you stack them a little too far apart, you get more gain, but you have more lobes in the pattern.
Yes, so Mark says, in particular, is designing such a phasing harness as simple as it seems, as simple as it seems mathematically, as it is in practice?
Well, what you need is a 1/4 of a wavelength in coax of 72 ohm coax. So you come in with 50 ohms. You have 2 pieces of coax that are 1/4 of a wave long in 75 ohm coax. Then you go to 2 pieces of 50 ohm coax, which are whatever length you need, but the same. When I built my EME array, the phasing lines were about 5.5 meters long, going to each of the 4 long Yagis. And using just a simple sweeper and dip technique, I was able to match all 4 lines to within 1 centimeter. That was perhaps a little pointless, but it was fun just to see how close I could get them.
Okay. Comment from Gareth G4XAT. Thanks for the pipe cap filters article, which I read recently. That's all of the questions that are up there at the moment.
Okay.
Okay then, if that's all the questions we've got this evening, just looking at the streaming service, and I don't see anything else coming up myself. So thank you, John, for reading those out. And I'd like to thank you, Kent, for a very, very interesting talk tonight, and that interesting little bit at the end with the history. I don't suppose most of us knew anything about that, but that was interesting little additional a bonus for us tonight.
Well, next time we can talk about when the B-17 did a loop coming back from a combat mission.
Right, okay. Really interesting. Okay, now this is the 4th talk in our series so far. Next month, unfortunately, we won't be able to bring you a talk. The main reason being that John, who controls everything, is not available. And unfortunately, our Zoom license does not allow anybody else to take control. John did originally think that we might be able to run it with John setting up the meeting, the streaming and everything, and just left it running for me to do all the introductions, etc. But I think tonight, with the technical problems we had at the beginning, just proved that if there's nobody at John's end to sort things out, we might be in trouble. So what we're going to do is we're not going to have a talk on the 10th of March, but we will try and organize something for the 2nd week in April, and we will announce that both in Scatterpoint, on our website, and on the Groups IO microwave reflector. So I'd like to thank you all for watching tonight, and we hopefully will see you back in April. Thank you, and good night from me.